get ready to be at attention, because hybridization, now that's a critical concept right there. It may have been covered to some extent in your general chemistry class, but I'm not going to treat it like review because it's deceptively complicated. It shouldn't be. I think once you get it and it clicks into place, you'll get it for good. But it will take some persistence to really grasp what's going on there. It's because it's a little abstract, right? But it's going to be a persistent theme. Get it now. We're going to spend a lot of time right now on it. So get it now. Do lots of problems right after this. Stick with it. You ready? Let's go. All right. So luckily in organic chemistry, our dive into hybridization discussions are simpler because we are not going to be talking about sp3d2 because D is not part of the discussion. So remember, when we talk about making covalent bonds, we're overlapping two orbitals. And since we're restricting ourselves to period 2 elements, we're really restricting ourselves to s orbitals, specifically 1s and 3p orbitals. So that massively limits our options. That's a good thing. That simplifies everything. So what are our options? Our options are the following: sp3 for a hybrid orbital, sp2, sp. What does that even mean? Well, taking it back even a step further, before the bond is made, you have atomic orbitals, pure, so-called pure orbitals, not hybridized, in other words. Not hybridized, not mixed. So these are our atomic orbitals, s or p. Atomic orbitals. Sometimes you'll see those abbreviated AOs. So those have not been in a bond yet. As they prepare to make a bond, notice how they're very different. So if you need electrons from both to make that bond, those bonds, and because you're going to add that many electron groups, they need a mix to make all things equal. And when you mix them, you get 3 possibilities: sp, sp2, sp3. Why are there 3 possibilities? It depends on how many of those p orbitals you pull in. But you always have an s orbital in there. Why? If you have a choice, you want something low energy or high energy, you're always going to choose the low energy option. Of the 2 orbitals, s or p, who's the low energy option? S. Notice its spherical shape. Who does it look like it's closer to? It lets those electrons be closer to the nucleus. That stabilizes them. Okay? Sorry, I put nucleus with a negative. That's something we do later. Closer nucleus. So, therefore, S is in everything. So you either, P is also, but it's either 1p, 2p's, or all 3p's. If you take all 3p's, you have sp3. So you have 1s and 3p orbitals. Remember, because there's px, py, pz. If you take only 2 of the 3p's, you have sp2. If you only need 1 of the 3p's, you have sp. So when you need all 3p's, that's plus the s, that means you had 4 total orbitals used. That means you had 4 electron groups to make bonds to, meaning you had, going back to VSEPR, tetrahedral electron geometry. If you did indeed take all of those p orbitals to make those hybrid orbitals, you should have 0 remaining p orbitals. Therefore, as expected, no pi bonds. Remember, p orbitals are used for pi bonds. Okay. Likewise, so we could also think of it like this. Here's what's available: SPX, SPY, SPZ, and we took them all. Let's do it again. SPX, SPY, SPZ, and we took 2 of them to get SP2. 1 left over for a p orbital. That means that something that's SP2 hybridized has a p orbital left over for pi bonds. Finally, if only one p orbital was taken out of the mix, so out of our assortment of possible p orbitals to use, that means we have 2 p orbitals left over. So it can actually make 2 pi bonds now. So we're going to go through each of those and show examples of that. This is just an overview so that we're comfortable seeing what you may, kind of recapping what you may have seen before, but if you haven't or you don't remember, don't worry, because we're going through this much more slowly on the next 2 pages. Now, notice they actually look the same, whether they have more p contribution or not. Okay. The one exception to this is that hydrogen never uses p orbitals. It only has an s orbital, so it will never use a p orbital make, or a p orbital make any bonds. So these are the 2 bonds you want to be familiar with when they make their overlap to make molecular orbitals. So a sigma bond comes from end-to-end overlap. So these are hybrid orbitals. Hybrid end to end. Do that with your arms. End to end. That's a sigma bond. That's what hybrid orbitals do. They make sigma bonds. They make the single bonds. Sigma bonding framework. The pi bonds overlap side to side. Do that with your arms. They have to be parallel. They do that. Which means if they're parallel, they have to also be in the same plane. So leftover p orbitals overlap to form pi bonds. I'm going to write that little note here. Must be parallel! Exclamation point. Okay. Let's label these orbitals. Let's even draw the orbitals when we're done. Okay, so it helps to think back to VSEPR because if we know how many electron groups it needs, we know which orbitals it needs, right? 4 electron groups means it needs 4 orbitals, means it's going to use all the 3 p orbitals combined, right? So easy part to start with is the H's. H's only use S, 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 S. Now, if you're not sure how to label those carbons, let's start drawing what's going on here first. Then we'll try to label them. So there's a carbon, and it's making a sigma bond with 3 H's. And then it has another bond to another carbon. Triple bond to carbon. I'll draw out all the bonds. Okay, now let's draw on those s orbitals and let them take up about half the space on the bond because we're going to let them overlap with an orbital from carbon. Remember, there's end-to-end overlap, and hydrogen always uses s orbitals. So we can label that S, S, S. Everywhere, we're going to label our s orbitals. Now, carbon's going to use a hybrid orbital. Hybrid orbitals look like a lopsided p orbital. We don't draw the other little tiny nub that was starting to get depleted. So remember, this is a p orbital, and this is a hybrid orbital. sp2, sp3, or sp. They all look like that. So we'll decide which one it is later, but we know that we're going to use a hybrid orbital to do our sigma bonds. So let's draw them in. Look like balloons, kind of, right there. Right there. And so let's label our sigma bonds. Sigma, sigma, that overlap there is a sigma bond. And then 2 hybrid orbitals overlap between the carbons to make that sigma bond. Look at this triple bond. What are we going to do here? In the triple bond, that means 2 of the bonds are pi bonds. Not using hybrid orbitals, they're using p orbitals. Let's take care of those later. Let's just worry about sigma bonds right now. All sigma bonds use hybrid orbitals except for hydrogen. So all the carbons are going to be using hybrid orbitals, and then the other, the heteroatoms as well. I'm going to just randomly pick the bottom one to be the one. It could have been the middle one, it could have been the top one. That part doesn't matter. Just one of the three needs to be the sigma bond. I'm going to let the other two represent our pi bond. So let's keep drawing hybrid orbitals to make sigma bonds. So there's that sigma bond. Balloon. Oops, I didn't let it overlap. Shame on me. Here we go. Overlap. Overlap. Label sigma, sigma, sigma. And all these H's have getting there, right? This is a beast of one. And oxygen needs a hybrid orbital as well. Has lone pairs too. We could draw those in. Label our sigma bonds. So one thing that kind of helps is now I can go to each carbon and say, how many sigma bonds did that carbon just make? Made 1, 2, 3, 4. So it needed 4 hybrid orbitals. So if it needed 4 hybrid orbitals, and it always uses an s, then it needed a px, a py, a pz. That gives me 4 atomic orbitals to mix together and make 4 hybrid orbitals. Because that's conserved. You always, if you start with 4, you end with 4. So 4. So that means it was sp3. Hence the tetrahedral affiliation, right? So let's denote that there, sp3. All right, how many sigma bonds did this carbon make? I'm still not to the pi bonds yet, but I noticed that it only made 2 sigma bonds, one on the side, one on the side. It's a linear geometry, right? One on the side, one on the side. If it only used 2, that means it used 1 s, and then it took only 1 p. Therefore, it's sp. Likewise with the other carbon that's part of the triple bond. Let's find all the other tetrahedral carbons. 4 sigma bonds means sp3, sp3, sp3. Now what about that oxygen? What's that oxygen doing? It made 2 sigma bonds. So we might say, oh, it's sp. But where are those lone pairs? They need a home. I mean, that's the definition of an orbital. Home for electrons, basically, right? Defining the space for electrons. So let's draw something in for them. So now we know we need 4, we have technically 4 electron groups. So we have 4 groups, 2 sigma bonds. Do we need to put those electrons in p orbitals? No, why would we do that? It's higher energy, right? We always want to have some s character there. So since we need 4 electron, we have 4 electron groups, we need 4 homes. We're going to use s and 3p, so that oxygen's sp3. Okay, the only pi bonds here are on the triple bond. Let's draw them in, and I'll do that in 2 different colors. I'll do the first one in blue. The first set needs to be parallel. There's 1 pi bond. Now I need to make, so let's say that was the px set of p orbitals. The next one has to be orthogonal to that. Good luck drawing that on paper. Wish me luck too. It's not always easy, but I just kind of make a diagonal and then try to connect them and indicate they're together. Color coding helps a lot. And there they are. So that accounts for all the bonds. You want to be able to do that. Practice doing that so that you can identify them more easily, okay? And so I've labeled it here. You can fill it in on the one above as well, just like we were starting to do. It's more thoroughly written out here though. Try that on another molecule. It's not always as simple as it looks watching me do it. We're going to do it a few more times for that reason and summarize it as well. Okay, so I like this summary table because it helps us remember what's going on when we decide what hybridization an atom is. So some of you might have taken issue with, how did I know oxygen was sp3? Right? How did I know that? How did I arrive at that? Did that make sense to you? Did you get that right away? So you kind of have to work through that by knowing which orbitals you needed to use. So I'm going to work through this methodically, the background theory of it, and then we're going to do another example, okay? So we're going to kind of go back and forth, because this does deserve that attention. Okay, so LCAO, which you may have heard of that acronym before, but I'll write it again in case you haven't. So LCAO is the linear combination of atomic orbitals. What does that mean? It means orbitals are conserved. No matter how you mix and match them for the purposes of hybridization, you don't lose any of them. They're conserved. So in other words, if you'd say I'm starting with an S and I'm going to make some more bonds, and so that means I'm going to need more orbitals. So I'm going to take a P. You don't get one big fat giant orbital. You get the same number of orbitals you took. So you took an S, you took a P, you get 2 SP. All right, let's do that. Say, conversely, you could say, how many bonds do I need? I know I need 2 bonds. I need 2 sigma bonds. Okay, so I'm going to start with lowest energy. I'll take an S. And then I'll just, I have no choice. I got to get a P. I have to take 2 orbitals because I need 2 bonds. So I'm going to mix them. And that means they're going to be SP, because those are the 2 letters I circled. Those will be for my sigma bonds. So number of bonds, I'm going to write sigma up here in that table. SP for sigma bonds. Okay. That means I have 2 p orbitals left over. So what happens when I mix them? Do I get 1 fat orbital once again? No. What does it look like? I get SP, a second SP, and then I get leftover P, leftover P. I had all the possibilities listed here, so those aren't there. So that's my new collection. So in summary, when you want to work that out, you won't have all these pictures available. Your thought process is, okay, I want to know what the hybridization is of this atom, or what hybrid orbitals it's using. We ask that a lot. So you'll say, how many bonds does that atom need to make? How many sigma bonds? 2. So if I know it needs to make 2, then I'm going to circle the first 2 orbitals. That means I have 2 separate sp hybrid orbitals. Carbon always makes 4 bonds, but if I only made 2 sigma bonds, that means the other 2 bonds must be pi bonds. So plus, that means more than likely, my leftover 2 p orbitals, leftover for pi bonding, okay? Or other things, you know, we'll talk about some other ways that we use p orbitals, but for right now, you might have only heard of using them for pi bonding. Now, what if you said, I see my carbon or my oxygen or my nitrogen using 3 sigma bonds? That means I need to circle the first 3 orbitals I see. That means I'll use an sp2. I circled 2 p orbitals, sp2, for my sigma bonds. Let's fill in a 2 now. I didn't fill in a 1 over there because we don't call it sp1, but sp2. How many sp2? 3 in equals 3 out. sp2, sp2. But I still have a leftover P that I didn't circle. So that's my new collection. So out of that assortment, that's what I have available for bonding. So if you want to work this out on your own, if you had to do the same logic, you might say, okay, I see that atom needs to make 3 sigma bonds. And here's what it has to choose from. It has an S and 3 Ps. So I'm going to circle the first 3 things because it needs 3 bonds. When I circle those 3 things, I see that I circle the letters S and 2 Ps. That makes sp2. Those represent my hybrid orbitals in use. How many of those? 3 separate sp2 orbitals. I know I need to make 4 bonds total. I need a full octet, or I need 4 electron groups total. So that means I need 1 p left orbital left over for holding a lone pair or for pi bonds. Okay, so we're limited in our scenarios. There's only one more scenario possible, is that we have 4 electron groups that create sigma bonds. So if I know I need 4 sigma bonds, I need my S and I need all my P's on board. Let's do blue. Circle the whole thing. That means I need my sp3. And how many of them? 4 in equals 4 out. sp3, 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 sp3. I took all of the p orbitals and hybridized them. There are 0 p orbitals left over. So let's summarize that. If you don't have beautifully drawn orbitals from a computer program like you do on this page, how do you work it out? You approach a problem, you say, I need to make 4 bonds. How do I work out its hybridization? Well, 4 bonds has these sp-pp to choose from. That means it needs all 4 of those orbitals. When I add that up, I get 4 different sp3 hybrid orbitals for my sigma bonds. Woo! Now that is really what's going on with the LCAO. Let me show you the LCAO in simpler terms. This is a good brain break and a drink break. See if you could see the analogy before I reveal what's going on here. Do I have space for this? I think I do. What do you think this might represent? This could be any of our second row elements. This is their orbital choices. S, px, py, pz. Here's our chocolate syrup. Here's our milk. So the p's are all the same, and S is different. S is clearly better because it's chocolate, right? So S is better. But let's suppose our goal is to make some chocolate milk. There's different ways to do that. We could say, well, we only need to use 2 glasses. So if we only need to split it between 2 glasses, we are going to save these for some other time. And we can mix it here. We can dump this in a blender and mix it up. Now notice the volume. This is full, this is full. So I don't have any other glasses available. That's why I said I don't get a giant orbital. These orbitals are the same size. So because these are full and they're the same size, when I mix it, I redistribute it again and I have a mixed result. So I go and I mix these. And LCAO, linear combination of atomic orbitals, voila, 2 in, 2 out. Now they're evenly distributed, equally chocolatey and milky. Here's my chocolate milk. But notice I have 2 completely undisturbed p orbitals. So these are available, these are pure p orbitals, pure milk, available for pi bonds. These are the hybridized, the mixed orbitals available for sigma bonding. What would be the hybridization in this chocolate milk pattern? 2 p orbitals left means I only used 1 p orbital. S and 1 p is sp. So what would sp2 look like? One of these is completely left alone. I don't touch it. But now the chocolate was mixed among these three. So make a prediction. Is it going to be more dilute chocolate? Yeah, right? Less chocolate character, if you will. Okay, so now notice 4 orbitals we started with. We ended with 4 orbitals. But look at the difference. Only one is still pure, p atomic orbital. Now we have 3 mixed orbitals, right? The volume stayed the same. The number of orbitals is conserved. We didn't get a giant orbital. Now, we did see a difference in the color. So it's still chocolate milk, but it's a lot lighter. So this is kind of like the chocolate milk I give my kids. Diluted a little extra to split among the 3 of them. And someday they'll notice that. Actually, they've already kind of noticed. Some of their friends say, wow, it's a light colored chocolate milk. But it can be lighter. How can it be lighter? If we had to split that chocolate syrup among all 4 glasses. So I'm going, of course, to show that, because why shouldn't this one also have the opportunity? But before I do that, let's remind ourselves what this hybridization would be. 3 got hybridized, 1 was P, so that means it can't be sp3. That means all 3 P's were hybridized. So take away a P, you got sp2. The S represents the chocolate. It's a little less chocolatey when it's sp2, more chocolatey when it's sp. We're going to go make sp3 now. That's the least chocolatey of all because it has the most P in it, or most milk rather, P character. So less S character. Who wants milk very faintly spiked with chocolate? So all 4 of these have the same color now. There's not a single pure one left. That would be your, but there's 4 in, an S, pure S, chocolate syrup, 3P, right? Milk, milk, milk. Mixes all together, that's what you get. 4 very dilute chocolate milks, or 4 hybrid orbitals, very dilute in S character. Cheers, salud, ching ching. So why are we spending so much time on this? You've seen nothing yet. We are going to discuss hybridization possibly every chapter. It's very much a foundational concept. We are going to want to, on the spot, use it fluently in the following way. We want to look at these carbons and say, there's a sp hybridized carbon right there. Which one would I be talking about? That one. There's a sp3 hybridized carbon right there. That one. Drill style, sp2. Okay. Another way you might see this listed in more formal terms is to describe all bonding. And so this is frequently a popular way to do an exam. Some of my old exams have done this, or homework problems, where we fully describe how all bonds and everything is, just to prove our ultimate understanding of this. So every carbon, it says to describe how all those 4 bonds are made. Okay, the atomic orbitals and molecular orbitals in geometry. Let's do that. So let's call this carbon 1, 2, and 3, and I'll show you that notation using that notation up here. Atomic orbital, atomic orbital. So C, sp2 to HS. So I'm going to do that with 3 times, carbon 1, carbon 2, and carbon 3. In fact, I'm going to do it 1 time, and I'll let you check your answers with the rest. That'll be homework for you. I'm going to do carbon 1, So notice we're always going to have 4 bonds. So let's start by listing the 4 bonds. Carbon 1, we have to do the orbital. What is the hybridization of carbon 1? sp2. It's using that sp2 hybrid orbital to make how many sigma bonds? 3 of them, because it's making 1 pi bond. So you're going to have CsP2 listed 3 times, plus, what's going to be that last bond carbon 1's making? A pi bond, right? P. So you always list carbon 1 4 times, and here's our parentheses, and then you're going to say what it's bound to. But that subscript will be different depending on what orbital it's using. So since we know it's making 1 pi bond and one of them's a p, and then because it's sp2 hybridized, the other 3, and the sp2 hybridized means it's using 1s, 2p, hence 3 orbitals make 3 sigma bonds, right? Now what is it bound to? It's bound to 2 h's, easy peasy. H uses s, hs. It's bound to carbon, number 2, 2 times. Carbon, carbon. But 2 different ways. 1 in a sigma bond, 1 in a pi bond. So these are all sigma, 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 pi. So carbon 2 is going to be pi down here, because that was what the other CP was. What is the hybridization of carbon 2? It's also sp2. So it's going to be using sp2 hybrid orbital to make its sigma bond with carbon 1. Give carbon 2 and 3 a try. Check back with me. See if you match. Okay. All right, here's a quicker summary table than the other one, but it's the same idea. Just because we want to be fast with this. Want to be doing this in your sleep. All right. In other words, we approach an atom in a larger molecule and we see it needs 4 sigma bonds. Then what do? We say, okay, it needs it all. If it needs it all, resulting hybrid orbitals, 4sp3. Number of p orbitals left over, 0. Total number of bonds, always 4. But let's be specific, 4 sigma. We approach a bond. We see it needs 3. Let's circle what it needs, 3. Look what I circled. I circled an S and 2 P's, i.e. sp2. How many of them? 3. Number of p orbitals left over. I didn't circle a p, one of the p's, so I get 1. So total number of bonds always is going to add to 4. 3 sigma plus 1 pi. Right? Okay. What else can I do? Approach an atom, see 2 bonds. Sigma bonds needed. 2. 2p. 2sp. 2 orbitals left over. Only 2 sigma bonds are used. Usually for carbon, that means there's 2 pi bonds made. Okay? So that sum adds up to 4 for 4 electron groups. Let's look at some harder hybridization. I think we're ready to level up, don't you? Level it up. What is the hybridization for these? Let's look at the carbon atoms and the oxygens. Okay, this carbon is sp2. That oxygen is 4 electron groups in it, right? It's making 1 sigma bond, 1 pi bond, and then its 2 lone pairs need homes. So it can be using a hybrid orbital for those lone pairs. So I'm going to write that. Lone pairs can use hybrid orbitals or p orbitals, but they need orbitals. Okay, so 1, 2, 3 electron groups that are sigma type bond electron groups, so for hybrid orbitals, in other words, and a pi bond. So take away a p for a pi bond. That's sp2. This one's probably a little easier because we see carbon only has 2 electron groups as a central atom. So that means it's making 2 sigma bonds. It means sp. Another way to look at it is say, hey, that carbon needs to make 2 pi bonds. Take away 2 p's. That leaves only 1 p to hybridize, S and p. And don't let charges throw you off, because you will need to be able to understand what's going on with charged species as well. So if something's charged, got a formal charge, so we already, this is the case that we saw in the first example, except it's charged. So that means there's 1 less lone pair. It doesn't change it, still sp2. It's just a matter of where the electrons are, whether they're bonding or lone pairs, but they still have 1 p being used for a pi bond. Same idea here. We have a negatively charged carbon, but we still have 4 groups around carbon. So we still need 4 orbitals. So it's still sp3. No reason for it to be otherwise. Now here is where we're going to level it up even more. This will be more of a challenge because it's going to tie in resonance. Another concept that's never going away with hybridization. So you got to be comfortable with resonance, and you got to be comfortable with hybridization to be comfortable with this problem. So you might want to break and come back before we do this one. Resonance plus hybridization, okay?
Yeah.